Hmm. Okay, welcome back, guys. I'm going to finish out the week by going over section 5.6, moments of inertia, center of mass and moments of inertia. You can think about this as an application of the integration techniques we've been working on for multivariable. Um, and I'm going to start by kind of just giving you the idea, and then we'll try to develop the math around it. I want to imagine we've got some kind of solid object suspended over maybe a pin. Here I'm representing something that's almost two-dimensional, like a thin plate. A lot of times people call this a thin plate. And we're imagining that the way the the pin that is under the plate has been positioned is such that it hits this sweet spot, this point, where the plate is balanced. Plate is balanced. So theoretically, there's kind of one exact point, right? There's one sweet spot where this is achieved. You may have seen this developed for one variable calculus in the past. And if you put a pair of axes at that point, so here I'm drawing a y-axis, here's my x-axis. The object has a tendency in general to want to tip, let's say, around the x-axis. So maybe it wants to tip down on that side, or maybe down on this side. All right, this is tipping about x-axis. And in theory, it might also have some tendency to tip or rotate about the y-axis. And both of these phenomena are stable when this object is balanced, tipping about y-axis. We're going to be able to describe this with these guys, center of mass and moments of inertia. One more idea. Um, that I would definitely hope you guys have seen before. So I'm going to put this one as recall. Recall. Let's imagine instead of this whole plate, I've decomposed into little particles of mass, little cubes, let's say, of mass. So here I've got one mass, M1. Maybe I'll put another mass. Uh, let's put it over here, M2. Let's imagine these all lie on a single axis. Any collection of point masses like this has somewhere a center of mass. Let's even throw in a couple more masses. Let's say maybe I've got one more over here, and this one can be smaller. Call that one M3. And then one more, we'll do one more big one over here. M4. So the center of mass in one dimension like this is the point where if all of these masses were attached by rods to this point, this whole bar would not rotate, right? It would be stable at this point, like a seesaw with the right amount of force on either side. So there's two things to take into account. There's the sizes or the weights of these various masses, and then there's how far any one of them is from this center point, right? So associated to M1, M2, M3, and M4, there are coordinates. Let's say X, this one's X3, X1, X2, X3, and X4, representing where they are on the line. If you call this center of mass coordinate X sub C, then it's in some sense this weighted average of the coordinates. So there's the amount of mass at M1, there's the position of that mass, and then on and up the chain, M2, X2, M3, X3, M4, X4. And then you want to divide by the total mass, let's say M1 plus M2 plus M3 plus M4, to kind of make it an average. Right, so this is something you would have seen before. That's the center of mass. Let's try to build just that idea right there for 2 dimensions and see where we can get. Um, yeah, let me try to redraw my plate now. So here is another plate. Whoops. This is integral calculus, somewhere we're going to be decomposing things into small pieces and taking a limit of some sort. So let's imagine we've broken this plate up into lots of little pieces. And we isolate one of these pieces. These are right here. Well, that piece, if we kind of, let's do it like a zoom in. Whoops. Let's zoom into this region here and just kind of blow that up. We've got this one piece of material. I'm going to put in quotes 2D because we're trying to think of it as 2D, even though it technically has that depth dimension as well. So it's got a delta X, it's got a delta Y. And in general, it's also got a density, right? And we're imagining maybe we've broken this piece up or this plate up into small enough pieces that over any one of these subsections, the density is roughly constant. We could represent that by, let's say, a function rho. And if the density is roughly constant, I can approximate it by sampling at a point, let's say xi, yi. By now, this should start, hopefully, this is looking like I'm approaching making some kind of an integral, right? Setting up all the basic components of an integral. But now there's a question you got to ask because you're in 2 dimensions, and you can ask it sort of like, well, along what axis am I concerned about balance? This could be balanced in one direction and maybe not balanced in another. So this one piece is contributing. I'm gonna say it as a kind of like an instinct or a willingness to tip. Let's say we'll do the x-axis first. About the x-axis, based on how far from the x-axis it is. Take a small moment to just ask yourself, if I'm interested in distance, sorry, if I'm interested in tipping about the x-axis, like in this picture, What quantity represents how far from the x-axis I am? It's the y-coordinate. There's one of these things where when we write this stuff out, you want to make sure you get the definitions right. So you put y where it's supposed to go and x where it's supposed to go. So there is this coordinate y telling me how far this little bit of mass is from the x-axis. So I can develop a concept of, sorry, wrong variable there. Um, X bar, I'll call it X bar. A concept almost of center of mass, but only with respect to the x-axis by taking, well, okay, I'm jumping the gun here. Let me do it, let me write it this way. I'm going to call it delta X bar. So it's just for this one piece. Well, I've got a density and an area. This collectively is a little bit of mass. I'm going to call that delta M. This is parallel to those little rectangular cubes I was drawing a moment ago. So this is one little bit of mass, just like those were all little bits of mass. And then there's this coordinate, well, I'll call it just yi, how far we are from the x-axis. And that whole quantity right there, yi times the mass, is like one of these quantities up here. So now I can devise this object. I'm going to call it X bar. And I'm going to put I'll put the limit right in. We've done a ton of integration at this point, so I think you guys can tell where I'm going with this. But right, the limit n approaches infinity, and I'm going to add up a whole ton of these guys at all these. So I equals 1 to n, j equals 1 to n. We're going to go over the entire object, the whole plate. And I want to, for every single point that I go to, for every single little subsection that I am analyzing, I want that y coordinate. I want this rough approximation to the density in the plate, or in that piece of plate, and I want the little bit of area. So collectively, this little chunk here is an amount of mass. This is my y coordinate. This converges to an integral, right? We're going to see an integral, a double integral. I'll just put over R, the region that represents the plate. Y times the density with respect to the area. And this quantity has a name. The first moment about the x-axis. One second, guys. Yeah, I think they don't. Do they say this out loud in the section? Yeah, so I don't know if they say out loud in this section that we call this the first moment. They just, let me go a step further. I'll tell you what just threw me off. Okay, there's a second coordinate y bar, right? So I can also integrate over the entire region, the quantity x. This is representation of how far from the y-axis I am, again, with respect to the density. And I get this other coordinate, x, y bar, and the pair, x bar, y bar, this is the center of mass. But it looks like in that section, they don't take the time to say separately, this is the first moment about the x-axis, this is the first moment of the y-axis. Okay, let me just take a step back. So in one dimension, the center of mass is found by finding an average coordinate on a given axis. So it's average x coordinate. Now we've gone to two dimensions and we've found two separate kinds of average coordinate. There's an average y coordinate and an average x coordinate. And that pair, x bar, y bar. So let's go back over here now. Here's what that's saying. Just imagine it about one little sliver. You isolated only this region here, all of those little bits of mass right there. And you found that average y coordinate, like I just wrote out down here, you would find a single point. If you did this along a different sliver, you would find a different point. Just kind of indicate a few more of them. There's all these points, like so. And then if you added all of those up and averaged them, you would get one single point. Maybe like right here. It's really just the y-axis that I'm drawing. You would have to repeat this whole process in the y direction. So you find, let's do a different color. For each one of these chunks, you find a different center. This is when you're averaging the x coordinate. And then all of those get added up to a single x coordinate. So there's my x coordinate. Here's my y coordinate. But I drew this well. It should be the case that the pair intersects right at the center of mass. Although the way I drew this doesn't necessarily look so good. Come on, center of mass. Okay. I mean, in some sense, we're just asking you to integrate the average x coordinate, the average y coordinate, and write the pair out. So let's try to do an example and see this all unfold. Example. So they give us a quote unquote triangular lamina. This is just a vocab word for a little plate that's shaped like a triangle. It gives us the vertices of this triangle. So 0, 0, 0, 3, and 3, 0. 0, 3, and 3, 0. And it gives us a density. Technically, when we start getting into physical quantities, you want to put units in there. So they tell us the density is x, y, kilograms per meter squared. I'm not really concerned with this part. I'm going to ignore it for the rest of the problem. We really just care about the function. So the first thing they ask us to do is A, find the total mass. Oh, I just made a mistake. Sorry. I just made a mistake. I'll have to go back and fix something. I apologize for that. I made one. It's kind of a major mistake. Sorry, guys. Okay, this guy here, and this and this and this. I'm gonna call this MX. This is the moment, the first moment about the x-axis and the first moment about the y-axis. But there's one thing that I didn't do, that I didn't incorporate. Go back up over here. To find the average coordinate in a given direction, you want to divide by the total mass. So let me just say real quick, there's one more quantity I didn't write. It's the total mass coming just from the integrating the density over the region. And then those coordinates, the x and y coordinates of the center of mass, they come from taking these moments and dividing by the total mass. Right? For the exact same reason that up here I divided by the total mass. Is to make it an average. Okay, now where is my, oh, it's right there. Okay. Okay, so let's just start by just finding the total mass. Boom, boom, boom. Call that three. Call that three. So here's the triangular plate that they gave us. I simply want to integrate the density over this shape. It's symmetric, so you can do it as a type 1 or a type 2 integral. I'll take x from 0 to 3, y from 0 to 3 minus x. The density is xy, and then that's dy dx. All right, we'll just get this done real quick. Xy squared over 2, 0 to 3 minus x. Um, Oops, why did I just do that? Whoops. XY, so y squared over 2, which is 3 minus x is 9 minus 6x plus x squared. Okay, let's pull up the 1/2. I want to integrate x cubed. I want to integrate minus 6x squared. And I want to integrate 9x. All right, this is a bunch. Let's see here. 27, 81. 81 fourths and 81 halves is 81 and 3 fourths. This is a lot of okay, let's see where we go with this. I'll do it all. Hold on. 81 halves, 81 fourths. Let's just do it all. Okay, this is 243 over this here is uh 254 times 4 is 216, sorry. Somehow this looks, maybe get 27 over 8. Okay, 27 over 8. So that's how much the plate weighs. Go a little farther. Find the moments X and Y. So that was A there. Let's try B. Find MX and MY. So all I want to do is kind of the same calculation more or less, but I need to incorporate one more factor of X or Y appropriately. So MX now, I want to integrate over the region Y times the density. So let's try to set that up. 0 to 3, 0 to 3 minus X. The density alone was XY. But now I've got to multiply by an extra factor of Y. This is going to be too much for me to do in my head, but so I've got a y squared. So this is now xy cubed over 3 from 0 to 3 minus x dx. This is the same as 0 to 3 minus x cubed over 3. Oh, there is a way I can do this that's easier, actually, I think. Does that work? Um, no, that doesn't work. Yeah, I don't want to write out this expansion, so I'm just gonna go and take it from the book. 81 over 20. Great. So if you expand this, we're gonna get as high as powers of 5 because the previous example had as high as powers of 4. I don't want to try to write all that out. You guys have calculators. And then my, so the same idea now, but instead of the average y coordinate, we're finding the average x coordinate still against the density. And then this amounts in practice to that extra factor of x appearing. And then this is symmetric. So whatever answer we got here, we have to get on this side as well. 81 over 20. Okay, that's A and B. And then we'll put C maybe down here. It's kind of the easiest one. Find the center of mass. Well, we've got the total mass, 27 over 8. And we've got these moments. And all we need to recall is that dividing by the total mass gives us these final answers. So I've got this average x coordinate coming from mx divided by m, which is 81 over 20 times 8 over 27. 81 over 27 is just 3. And then we've got is that 2/5? Yeah, 6/5. Again, by symmetry, we're gonna get the same answer on the second part, 6/5. If you put these coordinates together, you get the center of mass. They call it COM. Let's go back up to that plate real quick. Where was that? Right here. If this is 3, maybe that's 1. Where is 6/5, 6/5? It's maybe somewhere like here and there. And let me just ask you real quick. Does that look to your eye like the center in some sense of that triangle? Where we took all this work, or we did all this work to find these coordinates, and that does not look to me, I don't think, like the center of this object. I wonder if you can explain why that's true. Here's why. It's because the density we're working with is a non-constant density. XY as a function is very sparse or very small near the origin. But as we get out farther from the origin where X and Y can both get bigger, the product XY gets bigger and the density is higher. So this object is very dense along this edge here. but much less so uh, as we go toward the origin. And so it forces the center of mass kind of in the direction of all that density. What if I wanted the actual center of the object? We take rho to be a constant. Any constant is fine, but take the rho to equal one everywhere. It's a constant density. So we take rho. The resulting center of mass is called the centroid. Centroid. So if you find the center of mass for of the region R of the region R, if you have a geometric, you're given some kind of a shape, a triangle, a rectangle, something weird, and you find the center of mass for that shape under the assumption that the density is constant, you get a point that's a geometric property of the shape, that point. And it's called the centroid. Should I just do one example where we do that? And then I'm going to proceed. Let's do, where is it? Yeah, this guy right here. Another example. They give us this graph, y equals e to the x. Here's my y equals e to the x. They want us to go as far as 3 comma 0. Uh, and they want us to start at 1. So we'll start at 1. 1 comma 0. Okay. So they've given us this little shape here. And they ask us to find the centroid. They don't tell us any density, right? They just say find the centroid. You've got to infer or remember or whatever that you are basically expected to take the density to be 1. You can use any constant you want again, but one is usually the best. Okay. They're going to want us to set up double integrals over this region. You can tell, hopefully, this is a type 1 region. I can take x from 1 to 3 and integrate y from 0 to e to the x. Let's just throw that density in there, 1 dy dx. This is going to give me the total mass of this object. Uh, this is integral 1 to 3 of, it's just going to be e to the x. And then that comes out to be e to the 3 minus e to the 1. Or e times e squared minus 1. E squared minus 1. Okay, that's our total mass. We've also got these moments, moment about the x-axis, moment of the y-axis. You can always think about this as taking the same integral you already set up, the same density you already had, and for m sub x, multiplying in by an extra factor of y dy dx. Let's get this one out of the way. So that's y squared over 2. There you go. That's y squared over 2. So that's one half or one half. E to the 6 minus e to the 0. All right, that's what you're one. Whoops, sorry. E to the 2. Okay, e to the 2 over 2 e to the 4 minus 1. One more, my. Same idea. 1, 2, 3, 0 to e to the x. But now I'm multiplying by an extra factor of x. This is the same as 1, 2, 3, x e to the x dx. And then I always forget this. Is it uh, x minus 1 e to the x? Yeah, sounds right to me. Let's just check. If you differentiate that, yes. If you differentiate that, yes, they cancel. Yeah, that looks good. Yeah. Okay, this comes out to be uh 2 e cubed, and then the 1 gives us just 0. Nice and simple. Okay, making progress. The centroid for this shape is given by the average x coordinate, mx over m, the average y coordinate, my over m. These guys come out to be something obnoxious because this problem's got a lot going on. We're dividing by m, so e over 2. E to the fourth minus 1 is e squared minus 1, e squared plus 1. So that e squared minus 1 will cancel, so we'll just get e squared plus 1. And then for y, I want, oh, I did this wrong. Sorry. Whoops. This is terrible. Terrible, terrible, terrible. This is the average y coordinate. This is the average x coordinate. Uh, the my is the average x coordinate. Now I want my 2e cubed. Okay, so this is 2e squared over e squared minus 1. All right, this is 2e cubed divided by e is 2e squared. E squared minus 1, yeah. Okay, so then the center of mass is given by this obnoxious expression here. Okay, so one more idea I want to cover, and we'll call it. One second. Yeah. So they also call this the second moment, but this is also called the moment of inertia. Second moment, moment of inertia. Let's do one more recall. Go back to those centers, those little point masses I drew in 1D. Let me just do two of them now. This is M1. This is M2. And let's say this is 0 here. So this has an x2 coordinate, this has an x1 coordinate. If instead of taking x1, m1, and x 2m2 and dividing by the total. If instead we squared x1 and then x2, oh girl, this gives us the second moment. So this will come out to be I think they call this I. I'm gonna just call it I in one dimension is the moment of inertia. Oops. So to extend the this idea to two dimensions, we have two of these guys. I'm kind of just jump past all the build up because this is stuff that I just did for the first moment, but we're gonna instead of finding the average x coordinate, we're gonna find the average value of x squared. So we're averaging the first squared coordinate. If you average the x coordinate, that's about the y axis. If you average the y coordinate, that's about the x axis. And then there's one more to throw in there. And that's what happens is if you add them together, you actually get the moment about the origin. And I'm skipping. Oh, that's that. Yeah, that's right. Yep. Good. Let me just see here. Yeah, let's just do one quick example. I think it was a different triangular lamina here. Coordinates 0, 0, 2, 2, 20. I think it was that same density, XY. And they ask us to find the three quantities I just wrote out. I sub X, I sub Y, and I sub 0. Well, let's just try to go right for it. I sub Y, I want a double integral over this region. I'll do 0 to 2, 0 to 2 minus X. My density is XY, but I need two more factors of X here. 0 to, oh, blah, blah, blah. I'm integrating Y. The Y integrates the Y squared over 2, hence the over 2 right there. And then Y squared, we're going to plug in 2 minus X. You square that, you get this. Now we can write this one out, but I'm going to pull out that 1/2. And now I've got integrating X to the 5th, X to the 6 over 6, minus 2X to the 4th integrates minus 2X to the 5th over 5, plus 4X cubed. That goes to X to the 4th. 0 to 2. Now, if you plug in 2, I got, 2 to the 6th, 2 to the 5th, 2 to the 4th, but I've got a 2 on the outside in the denominator, 1/2. So we can reduce all of these. So 2 to the 5th is 32 over, we get over 6 there. 2 to the fourth plus one more two right there is again 2 to the fifth. And then we've got plus 16. If you plug in 0 everywhere for x, you're going to get 0. And that's still supposed to be 5 down there. This looks kind of like a ridiculous number to me. Let's see here. Uh, just 32 over. So this is equals 16 minus 32 over 30 equals 16 minus 16 over 15. Divided 15. That doesn't look right to me. I think I made a mistake somewhere. 1 second. Where's my mistake? X cubed y squared over 2. That be correct. Because geez, that's terrible. This should have been a 4 here. That's a 4. That's a 4. This is now 64. Just erase from here. Mm, mm. Let me just try to simplify some things here. Doesn't look good. X to the fifth, yes. So then this one was x to the fourth over 5. Yes. Okay. 4 times 16 is 64. So I get 64 times 1/3 minus 1/5, which is 2/15. This is still not correct. Uh, oh, that's why. That's why. I didn't draw out the region. In my head, I'm doing if this is 2 and this is 2. So, okay, let me just change this example a little bit. If you include 0, 0 down here and you get this triangular region here, the appropriate bounds of integration for that region are, like I just did, 0 to 2, 0 to 2 minus x, dy dx. That's not what they gave us. They include this 2, 2 here. So let me go and change that. Let's say we wanted this region here. 0, 0. Oh no, one more. Sorry, still wrong. Still wrong. My bad, guys. 0, 0, 2, 2. Yeah, there you go. This is much easier to integrate over. This is now 0 to 2, 0 to x, dy dx. So this is not wrong over here. It's just for the black region. If you wanted to do the orange region, let me just do this real quick. 0 to 2, 0 to x cubed y dy dx. This is much easier. This is 0 to 2. Y squared over 2 is x to the fifth over 2. This is now x to the 6 over 6. So that's I lose 2 powers, x to the fourth. That's this is squared 16 thirds. This is IY. Let me continue with this one because this is the one that appears in the book. And also, of course, it's much easier. If instead I put in 2 more factors of y squared, now I'm integrating y cubed. So this is y to the fourth over 4. Plug in x to the fifth over 4 integrates to the x to the 6 over 24 from 0 to 2. So 3 powers. This is 8 thirds. And then just one more. If you just add these guys together, you get that moment about the origin, 24 thirds. I sub 0. Okay, I didn't do a great job of this just now in these examples, but make sure in your own work to keep in mind every time you use a sub y on the outside, I sub y, m sub y, etc., it's the x coordinate that's going up by some number of powers, and then vice versa with the sub x on the outside, that's the y power. Also, another thing I didn't do a good job of, but you want to keep in mind is when you find coordinates, x bar, y bar, like I did over here, always make sure you're dividing by that total mass. If you don't divide by that total mass, you don't actually find the center of mass you're looking for. And then one last thing just to keep in mind is this is a vocab word here. You see the word centroid, they don't provide you with a density. You're supposed to understand that you're finding the center of mass under the assumption of constant density. As a reminder of where we are, the course, you guys have a quiz on Monday. It's the last quiz. And then there will be a final on Friday. And then also now you should see there's a project posted on Canvas. And that's an extra credit project. If you want to work on that and you don't understand the wording or anything like that, feel free to email me and we can clarify it. But you should think about that as taking up as much space in your grade as one quiz or one homework. Yeah, email me if you have any questions, and thanks, guys.